Okay, right. So can you remember the things that we have discussed last time? Can you see my screen? Yes or no? Yes or no?
Not yet, ma'am.
තමයි කතා කරන්නේ if නැත්තම් මම මේක නවත්තනවා. At least yes or no. So you can use chat box or you can just unmute your mic and speak.
Not yet, ma'am. Yes, madam.
No? Last time we discussed about the discuss about these things. Can you see? Bonds, chemical bonds. Can you remember? Can you see now? Yes, you can see. Thank you. Yes, these are the things, right? Right, type of bonds, chemical bonds, right? They are covalent bond, ionic bond, and dipole moment, and the concept of polarization, non-polar, how to find polar and non-polar molecules. At that time, you came up with some difficulties. That means how to find, how to correctly identify the geometry of the molecules. Can you remember? So you may think that all the molecules in a similar shape. That means in a round shape. Okay. So that is not true. Okay. So today we are going to discuss about those things, right? And the type of chemical bonds, especially hydrogen bond and other metallic bond. And these are the things, right? Okay. Right, okay. So this is very important part. As I told you previously, definitely there will be a question related to this section, right? At the end of the series or the end of the lectures, don't come and ask me what are the things comes to end semester examination, right? Okay. So the time to time, that means at the lectures. So I stressed this point, right? That means definitely they will come on your mid exam. Okay, right. So this is another important part. So today we are going to look at to understand the electron dot structures for the molecules, and then we are going to. So can you see my screen? So is there any problem with the logging? Is there any problem?
Yes, ma'am. Some
What is that? So you can why is that? So shall I send another link? It will take some time.
Excuse me, madam. Madam, there is a error in the login.
Oh, kata කරන්න
Some
කතා
students are
ටග්ගල්
showing
වැඩි
that
කරන්න ඕන
error
ටග්ගල්
message.
ඉවර කරන්න ඕන මම.
Even Shivanta is also.
ළමයි අඳුගරු බීරෝ වගේ ඉන්නේ නැතුව කතා කරන්නේ මොකද ප්‍රශ්නේ කියලා. ඔව් කියන්න දරුවෝ. So shall I send another new one? Shall I send another new link then? Can you join using that one?
There's a error message coming from when we are going to log in, madam. So, all right, madam. If it is send new
So
one,
I will
then
send another new link. Please
Okay,
stop
madam.
using that one.
Yes, madam.
Yes, okay. So I told you I went through the last slides, right? Few minutes ago, and today we are going to discuss about the electron dot structures, right? Last time, some students had problem how to identify the real geometry or the 3D shape of the molecule. So today we are going to look at that problem, right? Right, okay. So this is the topic, electron dot structure, right? So, so we are going to illustrate the electrons of the valence shell. Okay, valence shell of the atoms or molecules, right? So this is the way. So this structure, that means electron dot structure, used to illustrate or the visualize or depict the this physical arrangement of the atoms or the bonds respect to each other, right? That is the concept, the main thing. Okay, Lewis structure. So we call it as a Lewis structure or electron dot structure, right? So using this one, that means Lewis structure or the electron dot structure, we can visualize or we can represent the physical arrangement of the electrons in an atom or molecules, right? Or we can represent the bonds between these two atoms. Clear? But using this structure or the Lewis structure, we only represent not all the electrons, right? Not all the electrons, but the valence shell electrons of the atoms. right? Valence shell, right? Why is that? What is the importance? Why we represent the valence shell electrons? Because so those are the electrons contribute to bonding, right? They are the only electrons involved in bonding. Am I right? Yes. So please respond. Otherwise, it's very difficult to conduct online lectures, right? Okay. Understood? So this, the information actually, so that is the purpose, okay? So what is the importance of having this Lewis structure? So this the information obtained by using this Lewis structure or the electron dot structure, actually we can predict the reactivity or the intermolecular forces or molecular geometry, right? Using this, having knowledge regarding this Lewis structure. Someone's mic is on. Please unmute, please mute your mic. 11891190. So I ask you to rename your username using your registration number and your name, right? So I'm going to take the attendance for the regular lecture, right? Who is this Apple? Right? Okay, so right? So using this Lewis structure, actually we can detect, using this one, we can predict reactivity or intermolecular forces or molecular geometry, right? Let's see how to draw the Lewis structure, right? So this is an example. Hydrogen molecule, right? Hydrogen. We'll do together. So, right. Hydrogen molecule, okay? So how many electrons? How many electrons in valence shell?
1.
Yes, one. That is oneness, okay? Oneness.
Recording in progress.
So here, this is two hydrogen, right? Hydrogen gas, we are having two hydrogens. So one is in one S shell. So we can represent the electrons using this kind of a dot, right? Hydrogen like this, okay? So you can use different colors for these two. That means blue pen for this one and black one for this one, right? So this is hydrogen molecule, H2. Right? This is H2. Okay. So this is sharing. So what is this bond? What is the name of this bond? Write your answers in the chat box. Quickly. What is this bond? Sharing electrons. What is the name? What is the name? Sanjeeva, what is the name? Huh? Huh? Yes, Veerasinghe. Veerasinghe. Veerasinghe, what is the answer? Veerasinghe NN. So sharing electrons means what? Covalent bond. Okay, if you can't remember, please go through the lecture notes, right? Don't come to ask to have when you repeat the course, right? Don't come and ask what to do, right? So this is the time. Now you have enough time to study. Please refer the notes and you can read, you can find extra things from the internet and you can refer the books, right? Okay. So this is the way to illustrate the hydrogen molecules using Lewis structure, right? So shall we try another one, right? Right. So what about this chlorine atom? So first you have to find the number of electrons in the valence shell, right? Hydrogen is 1. So what about the chlorine? Chlorine. Huh? Chlorine. How many? 7 electrons, right? 17 group. It's in the 17 group. That means 7 electrons. Okay. So you can draw like this. Okay. 1, 2, I'm counting. Look at my mouse. 1, 2, 3, 4, 5, 6, 7. So this chlorine atom has 7 electrons and this one similar 7 electrons here. So it's very clear. It's used 2 different colors, right? Black and red. Right. So what happens when they are bonding the chlorine molecule? So this is chlorine atoms, this is chlorine molecule, right? 2 chlorine atoms. So they are sharing these 2 electrons. Okay. They are sharing these 2 electrons. Okay. This one. Right? Like this. Okay. Can you see? 2 different colors. Okay. So now, so this is covalent bond. Okay. So then can you count? So this one, this atom has 8 electrons. Can you count? 1, 2, 3, 4, 5, 6, 7, 8. Okay, this one also have 8 electrons. What about this one? This atom also having 8 electrons. Clear? Right? So this Lewis structure indicates that each chlorine atom has 3 pair of electrons. Can you see? 3 pair of electrons. So they are not used in bonding. What are those? Can you identify that 3 pairs of electrons? These are the 3 pairs of electrons. So they are not involved in bonding, right? So we call these as a long pairs. ekasara electron, right? Long pairs. So they are not used in bonding, right? And one shared pair of electrons, that is this one. These two, right? Can you see? Right? Clear? Am I clear to you?
Yes, madam.
Yes.
Yes, ma'am.
Thank you. Yes. So this is the way to draw the Lewis structure, right? Okay. We'll move. Right. So these are the steps that you have to follow, right? So these are what is these atoms? Homo or heteronuclear atoms? Homonuclear atoms. So these are homonuclear diatomic molecules. No problem with the selection. That means there are no any complicated. Select the central atom, right? So what about this kind of a things? Carbon dioxide, CO2, right? In the case like this, right? CO2. So CO2 molecule. So how to draw the Lewis structure, right? We'll go here. It says first identify the central atom of the molecules. So we have to identify the central atom of the molecules. Think about the carbon dioxide. Carbon O, so in the carbon dioxide CO2, right? This is the molecule, and we have to identify central atom. Carbon, oxygen. Among these three, you have to identify which atom comes central, right? මැදට එන්නේ මොකක්ද කියලා identify කරගන්න ඕනේ, right? Okay. So for that, here it say, so this is the least electronegative atom. Least electronegative atom. That means when you move from the periodic table, so the atoms away from the fluorine, okay? Fluorine is the highest electronegative atom. So when we moved away from the fluorine, the electronegativity decreases, right? So considering these two, oxygen and carbon, what is the least electronegative atom? Huh? What is the least electronegative atom? Quickly. I have to finish this part today. What is the least electronegative atom? So I asked you some students to do some parts. Present. Okay. So be prepared for that one. I will suddenly ask that students to do the lecture. That means do their presentation in the lecture period. Okay. Fair another. So this is remind. So I'm remind you to please ready for that one, right? I will suddenly ask, do this part like that. Okay. So what is the least electronegative atom comparing these two, carbon and oxygen? Huh? Hashini? Yes, carbon. Correct. Right. And then what is the next point? Assign the valence electrons to each atoms as depicted by the periodic table, placing 1 electrons at each. So they are. Then you have to assign the valence electrons, right? Then you have to assign valence electrons for each atom. So carbon, how many? 4 electrons. Oxygen, 6 electrons, right? So the third point is arrange the remaining atoms around the central atoms and join them to the central atom by a single bond. Okay. So then you have to arrange the atoms around the central atom and then join them to the central atom using the single bond. So here it says attaching hydrogen last is advised, right? So the more negative is someone's mic is on, right? Then you have to attach the other atoms to the central atom using single bonds. And then what is the next point? Long electrons. That is, here it says not long pairs. So long electrons indicate an ability to form more covalent bonds, right? Not long pairs, right? So resulting in either double or triple bonds, right? We can have single bond, right? You know what are the single bonds, but we can have either double or triple bond using these long electrons, right? We'll see how to form these double or triple bonds, right? So we'll do an example, then you can understand, right? So you can try this one, carbon dioxide, CO2, right? So you have to find the central atom, okay? Then try this one, carbon and oxygen, 2 oxygens there. So these are the valence electrons. So you have to draw these valence electrons first, okay? Right. Then the next step is join them using single bond. All right, like this, okay? Single bond using dash, right? Okay. So what happens? How many electrons now oxygen have? 1, 2, 3, 4, 5, 6, 7. Okay. So these are long pairs, right? These are long pairs. Okay. Ekasara electron yugalni. So this is the long electron. This one. මේ තමයි long electron එක, right? Now almost we complete single bond, okay? But we are unable to complete the octet configuration for these atoms. Am I right? Octet configuration එක නැහැ. Can you, do we have? Yes or no? Do we have for any atom?
No.
No, only 7, right? So what shall we do? So again, we can have bond using these two, right? We can have a bond using these two, right? Then that means double bond, okay? Double bond, okay? So in the case of double bond, actually, we are having sigma and 5. Sigma and 5 bond, okay? We'll look at this, what is this sigma and 5 bond later on. Okay, so this is the way forming double bond. Okay, so now can you count? Can you count the electrons? Here 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now the octet configuration fulfilled. Am I right? So you can check your work. Okay. So you can draw the Lewis structure using these things, dot and this kind of a dash or the straight line. Or else you can, I will accept both things, oxygen or this kind of dots structure, right? Carbon, carbon. Like this, okay? Okay, like this, okay? Dot structure and the dot and dash structure. Then you can check your work. So total valence electrons. How to find this one? Total valence electrons. What is this 4? 4 means number of valence electrons belongs to carbon. That is 4. We know that one. And plus, we are having 2 oxygen. That means 6 means valence electrons belongs to 1 oxygen atom. Then we are having 2. Altogether 16 electrons. Okay. So we are having 16 electrons. Right. For the double bond, how many electrons need for the double bond? We are having 2 double bonds. Right. 2 double bonds. How many electrons? 4. Right. 4. 4 into 2 means 8 electrons. 8 electrons allocate for these 2 double bonds. Right. How many electrons remaining? 16 minus 8 means we need to have another 8. So those electrons allocate for these long pairs, 4 long pairs. 1, 2, 3, 4. We are having 4 long pairs. Then altogether 8. 8 into 8, 16. Right? Right. Your answer is correct. Okay? Clear? Clear? Do you have any question? Yes or no? Hmm? Okay, thank you. Yes, we'll move. And here, the octet rule. So we discussed this. We are always discussing about this octet rule, but this is the point I introduced. But I haven't used any slide previously, right? So octet rule. So what do you mean by octet rule? So we know all the atoms wants to achieve the electron configuration of the noble elements. Am I right? That means 8 electrons in the valence shell. Okay, that is the norm. Most of the elements, especially S and P group, main group elements, they want to achieve the electron configuration related to the noble elements, noble gases. That means 8 electrons in the valence shell. Okay, 8 electrons in the valence shell. So that is called actually octet rule. So this octet rule indicates that atoms are stable, right? they are stable when their valence shells are filled with 8 electrons, right? So octet rule means, so they are stable. So that is a stable configuration. Okay. So this octet rule indicates that atoms are stable when their valence shells are filled with 8 electrons. Okay. So most of the elements in the periodic table, especially main group elements, that means those are belongs to S and P, right? S and P follow this rule, octet rule. Okay. So especially the octet rule applicable for the S and P group. Okay. What are things state here? So when we consider the halogen molecules, so the other halogen molecules form bonds like the chlorine molecule. So one single bond between atoms. Okay, 3 long pairs per atoms. Okay, like chlorine. Okay. So this allows each halogen atom to have a noble gas electron configuration. Okay. So general rule is an atom shares as many of its valence shell electrons as possible, right? Either until it has no more to share or until it reach an octet configuration. Clear? So that is a general rule. Okay. So these are the exception to the octet rule. So when I'm describing this one, so you may come up with some questions. What about the hydrogen and helium? So those, they don't have any, they only have 2 or 3 electrons, right? So the first shell, so they are actually only, they can only accommodate 2 electrons. Am I right? 1 is 2. Especially in the case of hydrogen, helium, lithium. Okay. The first shell, 1s2, 2s2, they only can accommodate 2 electrons. So they are actually, they are not following this octet rule. Okay. Hydrogen, helium, lithium. So they follow duet rule instead of the octet rule. Okay. Here. So the second point. The ions, atoms, and molecule contain unpaired valence electrons is called free radical. So this species disobey this. So there are actually, when we discussing, when we learn the polymers, okay, polymer molecules. So especially there are category or the things we call free radicals, unpaired valence electrons. Okay, so how the molecules, atoms, or the ions having these kind of free radicals, they are disobey this rule. Okay, and the helium, lithium, and hydrogen. And the other one is the transition elements. What are these transition elements? The elements belongs to most of the time D block, right? Scandium, vanadium, titanium, like this. Okay, transition elements do not obey the octet rule. Okay, they are having a large number of electrons in their valence shell. Okay. So they are actually valence shells of these atoms can hold 18 electrons, right? And then aromatic compound, C6, C6H6, benzene. So these kind of aromatic compounds. So because they are having delocalized of p electrons. So don't worry about these things. Just you have to know. So some main group elements follow the octet rule, but there are some exceptional cases like these kind of things. So you have to memorize 2 or 3 examples. So the atoms, the molecules with the free radicals, and the first group, that means lithium, hydrogen, helium, like that, and the transition elements and the aromatic compounds. Okay. Right. And another thing is sulfur and phosphorus. See, sulfur and phosphorus also sometimes uh, disobey this octet rule, because so we will see, sometimes we are having PCl5, PCl5 and SF6, sulfur hexafluoride. So this is phosphorus pentachloride, right? Okay. So here also, so these 2 elements also sometimes disobey this octet rule, right? Right. Okay. So the examples, group 4A, actually this should be corrected as 14. Okay. So nowadays we are using 13, 14, 15 like that. Okay. The group 14. Okay. So this should be 14. We are not using this 14. Okay. 14 and 16. Right. Okay. Right. So what is this compound? Methane, right? Methane. CH4, right? So these are the single bond. So this is the Lewis structure. So considering this hydrogen and carbon, the least electronegativity is, even though hydrogen, we assign hydrogen at the last. Okay. So then the carbon is the central atom. Then you have to arrange the remaining atoms around the carbon like this, right? So can you count all the carbon has its octet configuration, and also hydrogen also fulfilled their 2 electrons, right? And this is the water. Oxygen and 2 hydrogen, right? So like this. So we are having these things. So first you have to consider the valence electrons, right? 6. Then we need to have a 2 hydrogen like this, 2 hydrogen, and these are the long pairs. Okay. These are the examples. Here I took several examples, okay, with considering different groups. This is 6A. This is not 6A, 16. Okay. So this is another example group. So all these, this should be 1, 1, 1. Okay. 13, 14, 15, 16, 17, and 18. Okay. Don't use this 3A, 4A. Okay. Nowadays we are not using that nomenclature. Number of valence electrons. 13 means 3. 14 means 4. 15 means 4. 15 means 5. 16 means 6. Like that. Okay. So the number of bonds. They can have number of bonds like this. 3, 4, again 3, 2, 1, 0. Right. These are the example. Okay. So you can try. Okay. You can try. You can draw the Lewis structure for this compound. Okay. Draw the Lewis structure for this compound. So this is example for the oxygen. Oxygen. So this is the double bond. Right? This is double bond. Okay. Yes, 1172. Do you have any question? So this is double bond. Oxygen, right? All right. So you can draw electron dot structure for this compound. Okay. So this is the homework for you. Right? Clear? Now another one. So take note down these things, these molecules. I will ask one by one in the next time. Right? Draw the Lewis structure for these molecules. Right? Right? Shall I move? Have you not? Have you noted down these things? Okay, I will. Shall I move? Shall I move? Yes or no? Quickly. Yeah, thank you. Right. Okay. Read this one. Right. Molecular shape. Right. So the previous case, Lewis structure only we didn't think about the shape. Okay, just illustrate or represent the valence shell electrons. Right. From that we can represent the bonds, single bond, double bond, triple bond, right? So that is in the 2D dimension, right? But what about the molecular shape? So when we consider when we discussing the shape, we have to think about the 3D way. Am I right? So we are going to predict the molecular shape, right? We are the people going to predict the shape, right? Yes, we can. So for that, actually, we have to follow this model, VSEPR, right? So that means the valence shell electron pair repulsion model. What is that? Valence shell electron pair repulsion model. Okay. So this is a 3D shape. Okay. This is 3D shape. We are going to discuss about the 3D shape of the molecules. So actually it is based on the concept that electrons around the central atom, and it will configure themselves to minimize the repulsion. What is the repulsion? Where this repulsion occurs? Huh? What is the repulsion means? කොහෙන්ද මේ repulsion එකක් එන්නේ molecule එකට? We'll see, right? The name also says electron pair repulsion, right? So you can read this one, okay? Electrons in the bonds, and so in electrons we are having bonds and long pairs, right? In a molecule, in the Lewis structure we identify the possibilities. We can have long pairs, long electrons, and also what? Bonds, right? Am I right? These kind of a thing we can have. One, 160. Please mute your mic. 1160. Please mute your mic. Right? So there are several things. Okay. So there can be repulsion. Okay. So the geometry of the molecules arranged to minimize that repulsion. Right? We'll see. So how to minimize the repulsion between these two? That means long pairs and the bonds. How to minimize? This is the way. So the huge repulsion between long pairs, right? එකසර ඉලෙක්ට්‍රෝන අතර තමයි වැඩිම විකර්ෂණයක් තියෙන්නේ. Why? Always negative and negative. Right? Okay. And then long pairs and bond. Long pairs and bond. The minimum repulsion between bond and bond. Right? So you have to keep this in mind. Okay? Long pair, bond, and bond. Okay? We'll see how to predict the molecular geometry. So first it says draw a Lewis structure for the molecule ON in the question. First you have to draw the Lewis structure, right? That means there you can identify, as I told you, from the Lewis structure we can identify the molecular geometry. Then the first thing is you have to draw the Lewis structure. Okay. So then determine the number of electrons groups around the central atom. Each long pair of electrons count as a single group. Each bond count as a single group. Right? Keep it in mind. Even if it's a double or triple bond. we count bond as a single, even it is a double or single, right? So then the corresponding electron geometry can be selected through the table. I will show the table, right? So these are the steps that you have to follow. Right. Okay. Right. So here's the carbon dioxide. So this is the shape. So actually this is linear shape, because why? These are the long pairs, repulsion, the highest repulsion. So this in this degree, that means 180 degree. So we can minimize the repulsion. So this molecule lies in linear shape like this. Okay. So hydrogen cyanide also similar. Okay. Here you can see, so we'll see carbon dioxide. So first you have to draw the Lewis structure, and there, so you can count number of bonds. So first the things, draw the Lewis structure, and then second, you have to write number of, the second thing is number of bonds. Number of bonds, right? Number of bonds. How many bonds can you count? 1, 2. Okay, 2 bonds. Right? I told you, we count this as a 1. 2 bonds. Right? Then number of long pairs. Long pairs. Third point, not the third. Under 2, you have to mention this one, long pairs. Long pairs. Is 0 considered in a carbon. Okay. Then the shape, third one, shape of the molecule. So if I ask you to predict the geometry or the molecular shape, you have to write your answer according to these points, right? The marks will be allocated for these points, right? And also you have to draw the structure or draw the molecule, right? Shape. Shape now you can find from the table. That means number of bonds. Number of bonds and according to the long pairs. I will show the table. Right? Okay, can you see? Here it's the number of bonds. 2, Number of lone pairs 0, sorry. What is the molecular geometry? Linear. Right? So this is the example. Right? Clear? Right, we'll see. We'll go to another one. Right. Look at this one. This is the simple example. Boron trifluoride. Okay. Can you see? Can you hear me?
Yes, madam.
Yes, ma'am.
Yes. So here, BF3, right? BF3. So first you have to draw the Lewis structure and then, so this is, count the number of bonds. How many bonds? Boron වලට bonds කීයක් තියෙනවද? How many bonds?
3.
How many? 3. Right? 3 bonds. So there are no any long pairs. That means 3, 0. Long pair 0. The shape, what is the shape? Trigonal planar. Right? Try this one. Formaldehyde. CH2O. Formaldehyde. Try this one. So first you have to, what is the central atom? What is the central atom there? Quickly. Carbon. Yes, good. Carbon. Yes, carbon. And then we have to assign first oxygen and then at the last hydrogen. Right? Okay. Right. So we know we are having one here, 6, 6. So we can have single bond with the carbon and hydrogen, right? So how many electrons for the carbon now? 1, 2, 1, 2, 4. Okay. First you have to count the electrons, huh? Total electrons. Then we need another 4 to complete the octet structure. Then simply we can assign 2, 1 double bond, right? Then how many? Hmm? 1, 2, 3, 4, 5, 6, 7, 8. Complete. Right? Okay. So this is the now you can count this one. Count the bonds using this structure. Using this one. right? Count the number of bonds and number of long pairs. Count number of bonds.
Three.
Yes, 3. Good. Long pairs. Huh? Long pairs. Not any long pairs. Right? 3 and 0. What is the shape? Three and 0 means trigonal plane. Right? Right. SO2. Find the shape for the SO2, sulfur dioxide. Sulfur dioxide. Sulfur dioxide. Huh? What is the shape? SO2. SO2 කොහොමද? Lewis structure එක කොහොමද S වල? What is the central atom? Central atom is sulfur, right? And then oxygen. Oxygen. So how many valence electrons? එතකොට මෙතන 6 plus 6 into 2. 2 oxygen, right? 2 oxygen. And what about the sulfur? Again 6. 6 means what? How many? 18 electrons. 18 valence electrons. Okay. Right. So what are the possible ways? One bond. We are assigning one bond. Is that complete our requirement? මෙතන තියෙන එක valence එක. Right? මේ මන්ද හරිද? Is this correct? Look at my valence structure. Is this correct? Yes or no? Tell me. No, this is wrong. Why? Oxygen does not complete octet rule. Why? Let's count. 1, 2, 3, 4, 5, 6, 7. Only 7. This one also having 7. This one also having 7. So what is the possible way? We are having long electrons here, right? We can bond with this one and this is one. Bond with this one. Then what is the possible structure? Double bond with sulfur and oxygen. And then we are having one long pair on sulfur, right? So number of bonds. Number of bonds, quickly. Number of bonds, quickly. Tell me. Number of bonds?
2.
Yes, 2, correct. Number of bonds, then you have to write number of bonds to equal to 2 long pairs. Number of long pairs. Consider the sulfur 1, right? 1. Then we will look at the table. Number of bonds 2, number of lone pairs 1, altogether the electron cloud is 3, 2 plus 1, 3. That means this is the shape, bend. Why is that? So I told you the geometry or the shape of the molecules are arranged to minimize the repulsion between long pair bond. So here we are having long pair and bond. So to minimize that one, this is the angle of the atoms, right? Okay, bend. Clear? Likewise, shape, any bond, number of bond 4, tetrahedral for the methane, right? The number of bonds 4 means we can have number of bonds 3 plus 1 long pair. Then trigonal pyramidal for ammonia. Okay, ammonia. And 2, 2. Again, similar, very common example, hydrogen, water molecule, H2O. Okay, 2, 2, 2 long pairs. Oxygen have 2 long pairs. So the highest repulsion between these two, right? Then the shape is bend. So you have to memorize this table, right? I'm not giving this table at the exam. You have to memorize this one, right? Yes. Then 5, number of bonds 5. What happens? The different shapes. Trigon. Yes or no? Clear to you? Am I clear to you? Yes, you can. So I will give tutorial for this one. Okay. Right. We'll move to the next part. The more little bit. Yes. Yes. Do you have any question? Yes. Right. So I will move to this one. Molecular orbital theory. Right. So listen to me very carefully. Little bit difficult one. Right. Atomic orbitals. Okay. How to, when we try to configuration, right? So we discuss about atomic orbitals. Well, okay. So far, actually, today we actually discuss about the Lewis structure and the electron to VSEPR model. Okay, from these two actually, so we are trying to understand the electron distribution. Okay, so these are the simple way to predict the molecular shape, right? In the previous two sections, right? It says electron dot structure provide a simple way to predict the distribution of the valence electrons in a molecule. And this model that means VSEPR provides simple way to predict the molecular shape, right? So the molecular orbital theory assume that individual electron pairs are found in a molecular orbitals that are distributed over the entire molecule, right? So far, we try to predict the distribution of valence electrons and predict the molecular shape using the previous electron dot structure and this model, right? And in the previous lecture, or the how electrons localize, considering the atomic orbitals. Okay, atomic orbitals. We didn't discuss about the molecules. What happens? They are combined or had a bonds with each other, right? So today we are going to discuss that one. What happens when they form molecules, right? So the molecular orbital theory assumes that individual electron pairs are found in molecules orbital. Then we call it as the molecule orbitals, not the atomic orbitals. When we consider hydrogen H2, right? 2 atoms, and chlorine molecules, 2 chlorine, right? Water molecule, H2O. So they are molecules, right? So we are going to look at how electrons. So we are going to assign electrons to volume of space of a molecule orbitals, right? Clear? In the atomic orbitals, it describes the volume of space around the nucleus of an atom. Can you remember? Volume of space around the nucleus of an atom, right? There we discuss about an electron is likely to be found around the atom. Okay? Okay, don't worry. In the previous case, that can you remember the quantum theory? Can you remember the electron, how we assign electrons when we try to write the electron configuration? We use 1s2, 2s2, right? And we draw the atomic orbitals. Can you remember? So like this, atomic orbitals, these kind of a thing. 1s2, 2s2, 2p3, like this. These are the atomic orbitals. Right? Can you remember? So they are actually,
Yes, madam.
we discuss about considering atoms or elements, individual atoms, right? Now we are trying to study what happens to the molecules when they form bonds, right? Molecules like H2O, chlorine, Cl2, fluorine, F2, likewise, right? In the molecular orbital, now I'm talking about molecular orbitals, not the atomic orbitals, right? Molecular orbitals describe the volume of space around the molecular, right? Molecular, not the atoms, right? Molecular, where the electrons is likely to be found. right?
Recording stopped.
තේරුණාද ඉස්සෙල්ලම අපි කලින් කතා කරේ atomic orbitals ගැන. එතකොට ඒ අවස්ථාවේදී molecules නෙවෙයි අපි combine වෙච්ච එක දැන් සාමාන්‍ය if I describe the elements actually, you know, most of the elements we cannot find as a single atom. Can we? Sodium තියෙන්න පුළුවන්ද පරිසරයේ sodium විදියට? No, it cannot, right? Always sodium combined with an ion, right? Sodium chloride. So they are molecules. ඒවට තමයි අපි molecule කියන්නේ. Right? හරිද? දැන් අපි බලන්න යන්නේ molecule එකක electrons distribution එක. එහෙම නැත්නම් electrons පැතිරීම කොහොමද කියලා. Right? Understood? Yes or no? Right.
Recording in progress.
So this is the definition for the molecular orbitals. A molecule orbital describes the volume of space around the molecule where an electron is likely to be found. Okay. Right. So this is a little comparison between these two. Can you see? Molecular orbitals. Molecular orbitals are analogs to the atomic orbitals. They are analogs, right? Like atomic orbitals, molecular orbitals have specific size, shape, energy. Can you remember the atomic orbitals? SPD. Can you remember? We are having size, shape, and energy. Okay? Can you remember? SPDF, we discussed those things.
Yes, madam.
The number of molecular orbitals formed must equal to the number of atomic orbitals combined. Right? And then the next point. So molecular orbitals, just like the atomic orbitals, are arranged in order of increasing energy. Can you remember 1s2, 2s2, 2p, 3s, like that? Okay. Here the molecular orbitals also, they are also arranged in an increasing energy. The filling of the molecular orbitals is governed by the same principle as the filling of atomic orbitals. Same principle, like the atomic orbitals. Okay. So these are some comparison between the molecular orbitals and the atomic orbitals. Right. Here, read this blue color sentence. Right. So as I told you, electrons can act as a wave and particles, right? Here it says that when the two atomic orbitals combine to form molecular orbitals, right? So now we are discussing about deep things. We cannot actually see, right? What are happening, right? This is the inner case, right? So two atomic orbitals combine to form a molecular orbital, right? So the wave function. Previous case also we discussed about the wave function, right? Can you remember? In the atomic orbitals also I introduced these two words, wave function, right? So the wave function are combined both in phase and out of phase, right? I will show you a picture later on. So the wave function. So I told you in atomic orbitals. So actually Schrodinger equations we use for the wave function. Okay, don't think too much. Actually, in your level, you don't want to get too much. So there's a wave function. So the two possible things can happen. What is that? What is that? To form a molecular orbital, there should be a two atomic orbitals, and they can combine in phase and out of phase. I will show you. What is the result? What is the result? These are the results. Bonding molecular, sorry, one bonding molecular orbitals and one non-bonding molecular orbitals, right? These are the result. That's only, right? Clear? Am I clear to you? Don't worry about the wave function and wave solution, no. To form the molecular orbitals, two atomic orbitals have to combine. What are the possible possible ways in phase and out of phase? The wave can be combined. Both waves can in phase or out of phase. So there are two possible ways. So definitely we have to have two results. What are the two results? One thing, one bonding molecule orbital, that is respect to in phase case. That means two wave function, they are in phase. Okay. And if they are in out of phase, we can have anti-bonding molecular orbital. Clear? Right. We'll go. So this picture will help you to understand clearly. So these are so we called it as actually two words. We are using two words, right? So the molecular orbitals can combine, atomic orbitals can combine in two different ways, in phase and out of phase. In phase we called constructively. What happens in the constructive combination? Can you see? So this is the nucleus. For an example, hydrogen. So this is the nucleus of the hydrogen, right? Okay. So two waves. What happens? Constructive waves in your physics also you discuss constructive waves. Constructive waves, what happens? Both are in phase. What happens? Reinforce the wave, right? And bonding, wait. Yes, antibonding and non-bonding. We'll see. Yes, similar. So what happens? Constructive combination. What happens? Reinforce the wave, right? Destructive. Can you see the out of phase? Out of phase means like this. Here plus and this is minus. What happens? Cancel. Wave cancel each other. And there are no bond form. Okay. So this is destructive combination, right? So antibonding molecular orbital. So we use this sigma star, right? Sigma star. And bonding molecular orbital, we call it as a sigma, right? Sigma star, right? So the electron density of the orbital is concentrated between the atomic nucleus, right? Electron density. concentrate. Can you see? So this is the colored blue one, or the electron density. So you can see. So they are concentrated between these two nucleus, hydrogen nucleus. Clear? Okay. So what happens in the antibonding molecule? Antibonding or sigma star, the electron density of the orbital is concentrated in the region of space outside the area between the atomic nucleus. Right? Can you see? Right. Two waves with a different phase means it will cancel out, and this destructive type of interaction is called sigma star, antibonding orbital. Okay, right. Right, this is an example, right? We'll see how to describe this hydrogen molecule. Okay, so bonding in a hydrogen molecule. Some points are missing in my slide, so you have to note down, right? So you know hydrogen is 1s atom, only one electrons, and it is in 1s in the atomic orbitals. Okay. So these two hydrogen atoms similar, that means the atomic orbitals, electrons in the atomic orbitals 1s, right? What happens? So as the atomic orbitals move close together, so to form a bond, definitely these two atoms needs to come closer or move closer, right? So what happens to the atomic orbitals move close together? The amount of overlap increases until the orbitals combine to form molecular orbital. Right? What happens when these two atomic orbitals, 1s atomic orbitals moves together, the overlap increases until they form the molecular orbitals like this. So this is H2 molecule. Then what happens? Covalent bond is formed. You know what is the bond between these two? Covalent, sharing electrons, right? Then what happens when the covalent bond is formed? When two s atomic orbitals overlap. So we call it as a sigma bond. Single bond means sigma, right? Bonding molecule orbital, sigma, right? Okay, sigma bond. Right. So during the bond formation, during this bond formation, energy release. Why is that? Why is that? Energy release. Why is that? So the electron in each atom. So electrons, so we are discussing about the electrons. Electrons in the each atoms attract not only its own nucleus, but also the positive charge of the other atoms as well. Here. So this hydrogen atom have its nucleus and this one also have its nucleus. So this one not only in the nucleus, the electron cloud belongs to this hydrogen, not only attract this nucleus, but also the other nucleus of the atom, other nucleus of these hydrogen atoms, right? So the more orbitals overlap means more energy decreases until the atoms approach each other, right? So there is attraction, but another thing, there is a positive charge here and here. What happens? They are repelled. The two nucleus repel each other. So this repulsion causes a large increase of the energy. Two things can happen when they formed bonds. This electron clouds can attract this one, this nucleus, as well as this positive charge. That means positive nucleus can repel each other, right? So the maximum stability is achieved when when these two nuclei are in the certain distance, right? Understood? Am I clear?
Recording stopped.
දැන් මෙතන තියෙන ඉලෙක්ට්‍රෝන එකෙන් මෙයාව ආකර්ෂණය මේ නියෂ්ටිය ආකර්ෂණය කරනවා වගේම මේ නියෂ්ටියත් ආකර්ෂණය කරනවා. But what happens at the same time? These two nucleus repel each other, right? The stability එකට මේ දෙකම බලපානවා, right? උපරිම ස්ථායීතාවයක් එන්නේ මේ දෙක යම් කිසි දුරකින් තියෙනකොට විතරයි, right? Nucleus දෙකට එක ළඟට එකතු වෙන්න බෑ. මොකද repulsion එකක් තියෙන නිසා, right? So we call this distance
Recording in progress.
as a bond length, right? We call this as a bond length. For the hydrogen molecule, actually it's 0.74 angstrom bond length, right? Clear? Am I clear to you? Hello?
Yes.
Yes. Right, I will discuss only, I have. Shall I continue? Or are you tired? Huh? Shall I continue or shall I stop at this point? What about the others? All right. Okay, so I will stop here, right? And I will upload this slide to the LMS. And please go through this and then come to next class, right? So I will take after if we have mid-exam, most probably mid-exam will take 1 hour, and then I will take the other, the next, next hour for the regular lecture, right? Okay. Right. So do you have any questions or problems regarding today's discussion? Huh?
No, madam.
Right. Okay, then I will stop for today. And I will let you know the time and date for the mid-exam. Right. Thank you very much. Have a nice day.